We're ready to begin our 7th learning objective, in which we're going to learn to calculate the delta S of the system. We have previously learned to calculate the delta S of the surroundings from delta H. Here we're going to do it for the system. We have led up to this by learning about the third law of thermodynamics, and we are actually in this section going to be talking about doing it in standard state conditions. Here is our equation. The delta S of a reaction is going to be the sum of the entropies of products minus the sum of the entropies of the reactants. Now this equation will be very, very similar to one that you saw when you dealt with thermochemistry and learned to calculate the delta H of a reaction using the sum of the delta H of formation of products minus the sum of the delta H of formation of reactants. So we went to tables, we were able to obtain those values, and we always had to look up delta H's. But now that we know about the third law of thermodynamics, we know we can talk about just entropy. We don't have to look up delta S's, but just entropies of the products and the reactants. But the process is so very, very similar to what you did with delta H of a reaction. Because of that similarity, I will let you just go ahead and work a problem. In this problem, you are going to determine the delta S of the reaction that you see here. So go ahead and work it, and then we'll comment. Did you get 4 as your answer? Number 4 as your answer, which is 20 joules per Kelvin. If so, then you worked the equation correctly. If not, I will go through some common mistakes. One common mistake is that students do not incorporate that 2. They forget about the coefficients. So to get the delta S, we need to go 2 moles times the entropy of HCl. So that's one mistake that students make. Another common mistake as we continue on to this equation is they forget to subtract the sum of these two things. So it's the S of the H2, and you need to add that together with the S of the Cl2. Okay, so we have those that we would add together and then subtract. A common mistake is students will subtract the first and then add the second, but you can't subtract the first and then add the second. You won't want to do that. You want to subtract the sum of both of those. Now in that previous problem, and we'll look back at it here, we had 2 moles of gas on the left and we have 2 moles of gas on the right. But what would happen if we had a reaction in which the number of moles of gas is increasing from reactants to products? So maybe we start with 1 mole of gas on the left and we have 3 moles of gas on the right. That would lead to an increase in the number of moles of gas. What would you expect to be the sign of delta S in that case? Well, if you said positive, you'd be correct, because we know entropy of gases is far higher than entropies of solids and liquids. So if you're increasing how much gas you have in your reaction chamber, then you would have an increase in entropy. Now in that previous example, we have the same number of moles of gas, but we are seeing an increase in entropy. It's not a big increase, 20 joules per mole, but it is an increase. What do you think would lead to that increase in entropy? Well, it's molecular complexity. We have 2 moles of gas that are elements, and then we have 2 moles of gas that are compounds. So we've increased the molecular complexity, so we should see an increase in the entropy. Now let's go back and consider what would happen if we had a decrease in the number of moles of gas. Maybe your reaction had 4 moles of gas on the left-hand side of the equation, the reactant side, and you're producing 2 moles on the right. What would you expect? Well, in this case, it would be a negative change because the moles of gas is decreasing. One more problem for you to work, and here we're going to calculate the delta G of a reaction by going back to thinking of an equation that you learned, that the delta G of a reaction would be the delta H of the reaction minus T, the temperature, delta S of the reaction. Now that we've learned how to calculate the delta S of the reaction, and if we're given the delta H of a reaction, or we are forced to calculate it, we can get the delta G of a reaction and then determine whether a reaction is spontaneous or not. So calculate it. Did you come up with a negative 190.6 kilojoules? If so, you did it correctly. If not, here are some of the common mistakes. Did you remember to work in Kelvin? I gave it to you in Celsius, but you have to be working in Kelvin in that equation. If you didn't work in Kelvin, then you probably answered B. Did you watch your units? Another very common mistake of students is here is kilojoules, S or delta S is in joules. You have to make sure, if we're going to have our answer in kilojoules, that you've converted the entropy to kilojoules before you put it into the equation. And the last choice, if you selected D, maybe you didn't watch your sign here. We have got a negative sign, a minus there, and if you added instead of subtracted, you may have come up with answer D. So this is the end of learning objective number 7, in which we learn to calculate the delta S of a reaction by knowing the entropies of the products and the reactants. We also learned to predict the delta S sign just by looking at the moles of gas and whether it's increasing or decreasing. And lastly, we incorporated the delta S of a reaction into the equation that we see on this slide and obtain a value for the delta G of a reaction. We know that if the delta G is negative, as it is in this case, that the reaction will be spontaneous in the forward direction.